All right, so we've seen the rectangular window, and we derived its transform to be the alias sinc function. That makes sense because a continuous rectangle transforms to sinc, so a sampled rectangle should transform to async, alias sinc. And so there's the alias sinc looking for all the world like a sinc, but this one is periodic, so it smoothly goes from the right to the left. And then this is the real and even version, but we normally look at magnitude and phase, so here's the magnitude and here's the phase. So the phase alternates between 0 and pi, but the main thing, and this is constant throughout all zero phase windows, is that the main lobe has 0 phase. And so we're normally willing to completely ignore the side lobes. So the phase is 0 where it matters. And there it is on a log scale. And I'll remind you that the first side lobe is only 13 dB below the main lobe peak. And remember also that the roll-off is 6 dB per octave until the aliasing takes over and causes it to level off. As you increase the sampling rate, or the fundamental thing is the number of samples across the rectangle in the time domain. As that number increases, this will become 6 dB per octave roll-off. And we had our general theorem. Every continuous matching of derivatives gives you another 6. Every additional term in the Taylor expansion that is set to 0 in the leading in the leading Taylor order expansion terms of the window at its endpoint gives you another 6 dB per octave. So just to remind you, rectangle is discontinuous in amplitude. Triangle is discontinuous in slope, so that's another 6 dB per octave. So that's going to be minus 12 dB per octave, and so on. All right, so now the generalized Hamming family is something that I've introduced already. And remember that it's an async with 2 additional asyncs shifted over one bin of the critically sampled DFT, and same width. And in the time domain, that's a rectangle plus a cosine. So this is how you get your rectangularly windowed raised cosine window family. And you can see the benefit of using these 2 additional asyncs is that you can get some side lobe cancellation, and that's basically the idea. So you cancel some side lobes, you get them way down compared to the rectangular window, but you've doubled the window main lobe width. That's the fundamental trade-off of windows. We take a wider main lobe in return for less side lobe amplitude. Okay, so here it is analytically. Here's the generalized Hamming family written as alpha times async, which is the rectangular window transform, plus some beta times the rectangular window transform shifted over omega sub m. Remember, omega sub m is 2 pi over m. That's your sampling interval along the unit circle for a critically sampled window transform. So you shift it to the right and you shift it to the left and add it in with coefficients alpha and beta, and that's the family. And then if you inverse transform that using the appropriate Fourier theorems, then you derive the time domain function, which is the rectangular window times alpha plus 2 beta cosine 2 pi n over m. And so the alpha term is your rectangular window term. If beta is equal to 0, this reduces to the rectangular window. And when you set beta to something else, you get something like the Hahn window or the Hamming window. Those are the ones with names. So here's the Hahn window. Previously it was called the Hanning window, and I think that's just to make it sound more like Hamming. But it was introduced by Julius Hahn, no relation. And so people have gone back in more recent years to calling it the Hahn window. I mean, after all, he's the guy. And so you can also just call it a raised cosine. I tend to prefer generic names myself. So that's actually the simplest case, I would say, not counting the rectangular window, where you say alpha's a half and beta's a fourth, and then you get this nice trig identity that says you can say it's just a cosine squared. So a raised cosine is a cosine squared at half the frequency. I'm sorry, double the frequency. If you square a cosine, you double its frequency, and so to keep it at its original width, we have to divide by 2 in the argument when we square it. All right, so there's the plot of it, and remember, this is the one that is as smooth as it can be. It sets down as easily as it can on the edges, and that's what maximizes roll-off rate, okay? Because that's maximally smooth, tapered to 0, and so its roll-off rate is a whopping 18 dB per octave, right? Because that's a discontinuity not in amplitude, not in slope, but in curvature. So it's actually one more than the triangular window. So that's an 18 dB per octave roll-off. So it really rolls off. And I personally prefer these high roll-off rate windows because I just find them to be natural. You know, you've just got this natural high roll-off rate. And I guess another way of saying it is I don't like those discontinuities at the edge that are designed to minimize that outer side lobe. But let's go farther before I go into that.
To be natural from a mathematical standpoint or from perceptual?
Perceptual. So, let me get farther before we discuss that point. So the Hahn window properties are that the main lobe is doubled rectangular relative to the rectangular window. So the rectangular window, remember its first zero crossing was at 2 pi over m. So that the full main lobe width was twice that, or 4 pi over m. And at 2 pi over m is our capital omega sub m, our frequency domain sampling interval for the DFT of length m. Then you can write it as 4 omega sub m. And so now the side lobe is at minus 31 dB, whereas the rectangular window was only down 13 dB. So it's gone down, more than double in dB, which is excellent. And the roll-off rate is 3 times faster than that of the rectangular window. So that's pretty darn good. Now, Hamming is another member of this generalized Hamming family, where you set alpha to 0.54, not 0.5, and beta is 1 minus alpha over 2. So you keep the peak amplitude at 1. So you're basically over-raising it. And when you look at the transform, you can see that what you're getting for that is a much more uniform side lobe distribution. And so it's closer to an equal ripple side lobe, which you could then say would be kind of a Chebyshev optimality. So what it looks like it's trying to do is give you a Chebyshev FIR bandpass filter, where you have the narrowest possible bandpass around frequency 0, and then you want to minimize the side lobes. So minimizing side lobes in the Chebyshev sense means minimize the worst case side lobe. So you push whatever the highest side lobe is, you push that down, let the others come up until they're all equal ripple, until they're all equal in amplitude, and that's the Chebyshev solution. But you're constrained by the family. The form of the family is just a constant plus a cosine where there's one period across the window. That's the form of your window. It can't do anything but adjust those two gains. So basically the Hamming gets you close to the Chebyshev solution. So it gives you nearly equal ripple side lobes, at least at this length, and so you get this number. Now, just to show you how close it is to the optimal Chebyshev member of the family, here is the alpha that you get if you actually minimize the side lobe level within the family. And if you round that to 2 digits, you get the definition of the Hamming window. So I'm very comfortable thinking of the Hamming window as the Chebyshev generalized Hamming window. So within the family of generalized Hamming windows, it's the one that gets as close as it can to Chebyshev. So it's got this strange looking pestle. So you can still see it here. You can see that at the edge of the window, it just chops to 0. And it's that discontinuity that kicks up the higher side lobes and pushes down the nearest side lobe. So remember, for the Hahn window, the first side lobe is 31 dB down. Now we're down more than 40 dB. So we got more than a 9 dB gain in main lobe to side lobe ratio. Chet?
Explain the weird little wiggles on the first side lobe.
This distortion here?
Yeah.
To study that, I would want to compare it to denser sampling. So in other words, this is length 21, and I think I have that. So You know, it is basically an interference phenomenon. The side lobes, there is aliasing as well. But let's look at the higher, longer length and then think about it, see if it may be more clear. But yeah, there's this funny distortion at the beginning here. Okay, so the Hamming window has the properties that it's discontinuous. That means you expect 6 dB per octave. But wait a minute, we're not getting 6 dB per octave. It's pushing it toward uniform. Where's our 6 dB per octave roll-off? You know, we expect 6 dB per octave. But the aliasing is interfering with that. So what we need to do, again, is look at a longer window with more samples and verify that this 6 dB per octave does happen in the vicinity of the main lobe before aliasing is significant. And you saw the side lobe improvement. You saw that it's closer to equal ripple. And here's that question. How can the side lobes approximate equal ripple when, by construction, they must roll off at 6 dB per octave? Granted, there's aliasing, but there should be some 6 dB per octave action there. So what you do is you look at a longer window. So here's a much more densely sampled Hamming window. You see the same discontinuity. And now you see the main lobe, and you see this early lobe push down, but then you do see it settle into what is very nearly a 6 dB per octave roll-off. So you can verify that, you know, as the sampling density rises, you get this larger and larger region of 6 dB per octave roll-off before the aliasing causes it to level out. And then this struggle at the early side lobes, I mean, you know, clearly the optimality solution is giving you an interference in these early side lobes that pushes them maximally far down. And so, you know, it'd be very interesting to show analytically what's going on there. But intuitively, I think it has to do with the exact length of the window, which determines where the bends are. There's basically the FFT bends, and there's essentially the window bends, or the bends of the critically sampled FFT. And so the window transform is really best thought of on that length M frequency grid, and then we're superimposing this length N grid, and you know, that's a good thing to look into, just to intuitively see that.
But now we have new first side lobes, right, which are actually much lower.
Now we have what?
Before we said there's the main side lobe, which has 41 dB, but now if we look there closer, the first side lobe comes now very closer, and it's actually a bit lower, right?
It's now minus 42.7 dB. Right. So at the smaller length, it was minus 40.6. At this longer length, we're getting minus 42.7. So we're getting more side lobe rejection in the higher sampling density case. And that's because there's less aliasing. So that aliasing actually interfered with the side lobe level.
So we're more concerned with the worst side lobe, not the first side lobe. Usually they're the
Yeah.
same thing.
Did I say first? I meant to say peak.
No, I wasn't correcting you. I was just trying to solidify something.
Yeah. So for a Hamming window or for an optimal Chebyshev window, you're concerned about the worst case side lobe wherever it is.
And they usually find those through Parks McClellan or just trial and error?
This one is, you have to optimize over alpha. So it's just a line search on alpha. And you could use Parks McClellan here, but there's actually an official Chebyshev window, and it's pretty amazing, really, but it's known in closed form. You can just write it down. So maybe that's a good thing to jump to. Yeah, let's jump to the Chebyshev window since we've talked about it so much. Is it really that far away? Oh my gosh, we're not going to go through all this stuff. So, well, let me just first show you the window. So here's the Chebyshev window, and remarkably, it's known in closed form. So here it is set to be comparable to a Hamming window, because a Hamming window is roughly, a 40 dB side lobe. And this is the same length as our first example, 31, and 40 dB was roughly what it gave. And so you can see that it looks a lot like a Hamming window, but there's a very important difference, and that is that the endpoints of the window don't just drop off to 0. They actually go back up. They're actually impulsive. So the true Chebyshev window has impulsive endpoints. And so that's why it's not restricted to a 6 dB per octave roll-off. It can actually be flat. It can have 0 roll-off because it's got little impulses on the end. And you can really think of this impulse and this impulse as combining together to give you a cosine or whatever in the frequency domain, and that's what your ripple is. So your ripple is substantially a cosine created by those two impulses, but you can see that the zero crossings are not uniformly distributed. So the rest of the window does push the zero crossings around, but the side lobes are exactly equal ripple. So this is the optimal Chebyshev window, but we did not constrain it to be the member of any particular family. So it's not just a constant plus a cosine, it's whatever you want to do with those samples. You have capital M samples, you do anything you want with them. And another amazing thing about Chebyshev optimality is that it has these characterization theorems. So the Chebyshev optimal spectrum in this problem is known to be unique if you find the error alternating enough times. So it's a length 31 window. So that means in the frequency domain, you're adding together, a constant plus 30 complex sinusoids, or it's a constant plus 15 real sinusoids at different frequencies. And so finding the linear combinations of those that give you the optimal Chebyshev approximation to an impulse in the frequency domain, which is the main lobe and then these minimized side lobes, is uniquely characterized by having enough alternations in the error. So this is the famous Chebyshev alternation theorem, and it not only, if you find a function that does it, then that's the answer, and it's unique. There's no other, you found it, you can just stop searching. So that's just one of the magic things about Chebyshev optimality. And this has that property, so end of story. You don't have to go looking, you don't have to find any other way to do it. It's just the problem is solved and there is no other solution. So now you might think, well, where do you come up with that? I mean, I find this completely amazing myself. What an achievement of mathematical reasoning. Well, here's the answer. So it turns out the closed form answer is this. So you take your let's see. So you take your alpha, which is the side lobe level. So your side lobe level is minus 20 alpha, and that will basically force the main lobe to be a certain width. And so 10 to the alpha, hyperbolic inverse cosine of that, and then divide by your window length m, and that's this gamma function. And now you plug that in to this expression, which looks like a Chebyshev polynomial up here, and then you're dividing by the hyperbolic cosine of m times the hyperbolic inverse cosine of gamma, which is basically a normalization. And that is the closed form expression, and it has the right alternation, and so it is the unique optimal Chebyshev solution. And so you evaluate that on your FFT samples and then inverse FFT it, and that's it. So you just take the inverse DFT of this closed form expression sampled, and there it is. It just comes right out. And here's the problem that it solves, just the formal formulation of the Chebyshev optimality. And so you might think, where would you come up with these functions? And why would you guess that, right? Well, it actually comes out of Chebyshev polynomials. So, and the Chebyshev polynomials are, they have a long history in approximation of functions and so on. And so here is the Chebyshev polynomial of order 2. They're basically polynomials that oscillate between plus and minus 1 over the interval minus 1 to 1. And then outside of that interval, they just take off, right? Because they're polynomials. And so the second order one is this parabola here, and it just takes off. But in the interval minus 1 to 1, it goes from 1 to 0 to 1. I'm sorry, 1 to minus 1 to 1. The 0 line's in the middle here. So then you have your fourth order case and your sixth order case drawn here, just overlaid. And here's their analytic definition. And these have been studied quite a lot since hundreds of years ago. And so this is now the recursion that they satisfy. So there's a lot of mathematical results regarding Chebyshev polynomials. And you can form optimal Chebyshev approximations by projecting onto these Chebyshev polynomials. So the properties are that the T sub n is an nth order polynomial. If it's an even order, then you get an even function. If it's an odd order, you get an odd function. And then you'll have n zeros in the interval -1 to 1. And importantly, you have n plus 1 extrema. So you know that n plus 1 extrema will determine an nth order polynomial. So that means all of the zeros are in the interval. And this is that magic property that's used in proving Chebyshev optimality. So you can use these things to get the error to alternate the sufficient number of times to satisfy the alternation theorem in Chebyshev optimality, and then you know you've got the unique Chebyshev answer. Another property is that they're greater than 1 outside of that interval. So that's the Chebyshev window, and it doesn't usually work out like that. We don't normally get optimal windows in closed form, but when we do, it's really beautiful. All right, so back to the generalized Hamming family. Yeah, so I've got a few more windows I'd like to talk about. I can talk about them on Thursday, but yeah, what we just did, oh yeah, so we did the longer Hamming, didn't we? Yeah. Now I can't page. That's weird. Oh, I've got a stuck key, but it's a good one. So here, let me just close on this transform summary, which is to show the rectangular window, the Hahn window, and the Hamming window. And so the rectangular window has the narrowest main lobe, but the highest side lobes. The Hahn window has a doubled main lobe and the fastest possible roll-off rate, but only 31 dB rejection in the first side lobe. And then the Hamming window has substantially the same main lobe width as the Hahn. All members of the generalized Hamming family basically have a main lobe that is twice the width of a rectangular window, but the Hamming one gets you closest to Chebyshev, and you get more like 40 dB rejection, which is a good telephone quality window.
Getting back to what Chet asked earlier, would you mind explaining now why you think the Hahn window is a little more natural sounding?
Oh, so why do I like the Hahn window? I think it's best to look at it in the time domain, because you pick up a chunk of signal and multiply by your window, and my intuition is no discontinuities. Those that discontinuity that is giving you a more equal ripple spec in the side lobes is also giving you a click. That side lobe energy, the high frequency side lobe energy, is something I don't want to ever hear. I don't want to hear a click up there. Another way of thinking about it is that you normally have an auditory masking pattern around each frequency domain stimulus. So imagine now this is some frequency analysis, and so instead of 0, I have like 440 or some frequency. So this is the image of a sine wave at some frequency in the spectrum. So the difference between this Hamming and Hahn spectral image could be such that the masking pattern starts about you hear different numbers, but 10 to 20 dB below the main peak. So below this main peak, I could draw a masking pattern, and the masking pattern falls away from the peak, just like the side lobes do in the Hahn window. Whereas in the Hamming window, your masking pattern will decay, and then actually it might come under the side lobe. So it could very well be that you're going to hear these equal ripple side lobes because they exceed the masking threshold. So in audio, we're more likely to not want to be looking at the absolute level of the side lobe, but the side lobe to masking ratio. So you want to see what you really want to do is superimpose this with a masking pattern and push the side lobes below that. And I happen to recall that the very last slide says, oh, maybe it's the second one. There's a window by Dolby. I think they have a patent on this actually, and it optimizes the following. So it gives you a narrow time window. It gives you a smooth onset and decay, and this is the point I was just making. The side lobes are pushed below the worst case masking threshold. So it's not going for a uniform side lobe level or a particular roll-off rate. It's just saying push them down below the masking threshold. So it's purely a perceptually driven side lobe design, side lobe spec. And that's really what you want for audio. And so this is in one of the Dolby coders. You know, Dolby makes AC2, AC3, AC4. They sort of came along right around the same time as MPEG and MP3 is kind of a parallel development. You know, that Dolby AC coders were in parallel with the MPEG stuff. And then everything merged and standards evolved. So that's an introduction to window. We'll see some more.
Just a practical question. So I come from the ADC world, and there we try hard to make audio ADC with THD minus 110 dBs or so. And now we go into the audio processing and see windows with side lobes of minus 40 dBs, and then I'm wondering why doing the ADCs with 110 dB THD.
Wondering why you need what?
THD. So
Total harmonic distortion?
yes, because if I have a full scale input, means I have a sinusoid at minus 105 dB or so.
Mm-hmm.
And now we're making processing with windows which have 40 dB side lobes, so we'll never actually see one of those.
Right. Exactly. Well, you just proved that we don't want to try to get by with a Hamming window.
Okay.
Yeah, and that's why we need to look at more windows, and I'll finish with optimal windows. So this is one example of an optimal window, but I'm going to finish the discussion of windows with a discussion of how you optimize for whatever you want. We're going to look at optimal FIR filter design using convex optimization and that sort of thing. So ultimately, that's the answer for a really careful window in the audio world. But it's still worth it to look at all these classic windows. And the reasons are you're learning some Fourier theory. In other words, going back and forth between the time domain and the frequency domain and being able to understand side lobes and where they came from in the time domain and all these various relationships between shapes and time domain and frequency domain. Secondly, you're learning a lot of classic windows that you'll read about. And you'll find them in documentation. So any generally knowledgeable signal processing person needs to know what the Hamming window is and what the Blackman window is. You just need to be conversant in the field, right? And then third, we're going to learn a lot of interesting optimality relationships like the Dolph-Chebyshev window. There's some really interesting mathematical results that are also Fourier results, and they are also practical engineering tools. And they may not be the ideal answer for your perceptual audio application, but they're worth knowing for a number of other reasons, and they're just part of a general education in signal processing, audio signal processing as well. So that's why I'm dragging you through all the classic windows. And I find it interesting. I teach this stuff every year, and I never get tired of it. I think it's really cool. I think it's there's a lot of good results and great achievements in math and in engineering, and then perception comes into play. And you just build up a good, solid Fourier intuition from the study of windows almost by itself. You really can get a lot out of that. So I think it's really worth it.